Welcome to this explainer. Today we're tackling one of the absolute wildest frontiers in modern science, literally reverse engineering the human brain. But instead of dealing with biology and squishy organic tissue, we're actually doing it with raw electronics. We're going to explore exactly how building a brain from discrete circuit components is unlocking the deeply hidden secrets of our own cognition.
Okay, let's dive into this. We are completely reframing the concept of chaos today. Look, in neuroscience, if your brainwaves were perfectly regular and totally predictable, well, you actually wouldn't be able to process new information at all. Chaos is not a glitch in the system. It's a strict biological necessity. It's really this beautifully complex engine that drives a perfectly healthy mind.
So, here is our roadmap for today's explainer. First, we'll look at the brain's beautiful chaos. 2, we'll unpack the electronic brain toolkit. 3, wiring the neural network. 4, observing simulated chaos. And finally, number 5, why brain chaos matters. Let's get to it.
Section 1. The brain's beautiful chaos.
Now, studying a live human brain in real time is, as you can imagine, notoriously difficult to do without somehow altering the system itself. And that brings us to our core definition, brain chaos. This basically refers to the intricate, completely nonlinear dynamics and emergent behaviors that actually make up normal, healthy brain function. When neurons fire across synapses, it is not just some simple straight line. Without this beautifully complex chaos, our neural networks literally couldn't adapt to stimuli or learn a single thing.
Section 2. The Electronic Brain Toolkit. And this brilliantly illustrates our starting point. Because studying biological wetware is so incredibly tough, researchers just turn to hardware instead. What we're looking at here is a really foundational circuit layout that's designed to model those chaotic neural dynamics. Notice how the input voltages are passing through the R and C components. That's the resistors and capacitors, which are essentially acting as our neural pathways. Then the signal hits that GX element. That's our nonlinear function. This single, simple line is quite literally the backbone of our artificial neuron.
So zooming in on that g of x element, it relies on the FitzHugh-Nagumo or FHN function. I absolutely love this concept because it basically acts as the mathematical heartbeat of our electronic neuron. It specifically describes the dynamics of the system. It dictates the spiking membrane potential, meaning it strictly regulates how a neuron gets excited enough to fire and then exactly how it recovers to get ready for the very next spike.
Alongside that mathematical heartbeat, we also need the tunnel diode you're seeing right here. This little component possesses a totally wild property called negative differential resistance. Normally in electronics, as voltage goes up, current goes up, right? But here, as the voltage rises, the current actually drops, which honestly sounds like a completely broken circuit. But it is exactly the kind of nonlinearity we need. This specific unpredictability is what actually allows for complex learning.
So, to quickly summarize our toolkit, let's map these hardware equivalents directly to biology. The resistors and capacitors, those are our physical neural network pathways. The operational amplifiers, or op-amps, they're generating the actual behavior and simulating our variables. And those tunnel diodes are providing that crucial non-linearity for complex learning. These aren't just random spare parts. They are incredibly precise, highly functional stand-ins for actual brain matter.
Moving on to Section 3, Wiring the Neural Network.
To actually assemble this whole shebang, the researchers used a super rigorous 3-step methodology. Step 1, they started with computational software simulations, specifically a program called ISIS, just to mathematically model everything out. Step 2, they took those digital models into the real world, physically implementing them with real electronic components. And Step 3, they finally powered it all up to observe the synaptic connections and capture that elusive, chaotic behavior. It's literally taking pure math and translating it into a physical reality.
Now, what's really interesting about this slide is how they actually achieved this architecture. On one side here, we have the Chua circuit blueprint, which is totally famous in electrical engineering for its inherent chaotic properties. And right alongside it, the FitzHugh-Nagumo layout. By physically injecting the FHN model directly into the Chua circuit, these researchers successfully married a biological timing mechanism with a raw, unfiltered chaos generator. They quite literally wired an artificial brain.
Section 4. Observing Simulated Chaos.
Okay, this is the exact moment where the math turns into signals we can actually measure and see. Compare these two readouts. What we have on the left is a standard time domain waveform. It's completely regular, very repetitive, entirely predictable. But then, look at the right. We have this wildly converging chaos phase portrait.
Notice how it's bounded, yet geometrically incredibly complex, and it never perfectly repeats itself. This visually proves that true brain-like chaos is actively emerging from our circuit.
Building right on that, let's compare another chaotic signal to a stable chaos phase portrait. This really highlights such a delicate balance. You see, a healthy human brain is essentially a master tightrope walker. It is constantly balancing right on the razor's edge of converging chaos and stable chaos to maintain what we call dynamic stability. It absolutely must be stable enough to hold on to memories, but at the very same time, it has to be chaotic enough to adapt and learn instantly.
So, the crucial point is that this dynamic stability results in something truly incredible. Notice that beautiful double scroll pattern right in the center. This specific readout proves autosynchronization. We're talking about intermittent periods of totally coherent neural activity happening right smack in the middle of chaotic fluctuations. In a very real way, we are looking at the electrical signature of a simulated brain thinking. It is literally finding temporary meaning within an absolute sea of chaos.
Which brings us to our final section, number 5, why brain chaos matters.
The real-world impact of all this extends so far beyond the laboratory. First of all, it finally physically elucidates how biological neural networks process information. It physically maps dynamic stability against unexpected perturbations or trauma. And, absolutely critically for medicine, it helps us identify the specific disruptions that cause neurological disorders. Like for instance, did you know certain seizures are actually characterized by excessive stability? It's a dangerous lack of chaos. And beyond medicine, this work directly inspires and paves the way for advanced neuromorphic computing applications. We're talking about artificial intelligence based on physical, brain-like hardware, rather than just software code.
I want to leave you with a thought that really gets to the core of why this whole explainer is so profound. If just a handful of precisely arranged electrical components can successfully mimic the beautiful, totally unpredictable chaos of human cognition, what does that actually mean for the future of artificial intelligence? The line between biological brains and electrical circuits is blurring faster than ever before. Thank you so much for joining me for this explainer, and definitely keep exploring the incredible world of neurodynamics.